I just got back from an hour workshop in Britain, so if I fall asleep, it's not because you're boring. So yes, I'm talking about multiple imputation. We have lots of data ends up being collected with holes in it, and one of the things you can do is to just throw out all the records that have holes in them. That's bad, both because you lose a lot of data, and also because you end up with a biased selection of data. So an alternative is imputation, where you try and fill in the holes. The sort of simple ways to do that are to fill in the holes with the best guess at what the missing value is. That turns out to be a bad idea. So suppose you've got a data scientist and you're missing gender. If you fill in gender with your best guess, then as we've been told earlier, you're going to impute male for everybody. If you ask whether people are smokers or non-smokers, if you fill in your best guess, you're going to say everyone's a non-smoker, and so on. So the best guess imputation tends to stereotype things. You get the most common outcome rather than a realistic variation. And that's the point of multiple imputation. So the goal here is to replace each missing observation not with the most likely value, but with several values, a range of possible values sampled from some predictive model. So you have a model for how much you don't know about the variable, and then you sample several observations from that to get an idea of the actual uncertainty and variability. You end up then with multiple data sets, not just one data set, so you have to do your analysis multiple times, but that's not a big deal. You can do that. And as a result, valid inference is possible if you're clever and lucky, if you get a good model, which it really isn't for other forms of imputation. What we've been working on is to use machine learning algorithms to produce faster, more efficient ways of doing this to large data sets. So the sort of state-of-the-art methods involve taking each variable in your data set and constructing a model for that variable given all the other variables, and then iterating that. As the data set gets bigger, you need more and more models, and each one takes longer to fit, and the whole thing gets slow. Smoke comes out of the computer and so on. And so what we hope is that by using reasonably fast and automated machine learning algorithms, we can get good multiple imputation results on large data sets. The other thing about large data sets is that you can't put, if you've got 1,000 variables, you can't put a lot of human effort into modeling each one. So you need something that's reasonably automated. The challenges, there's a lot of hyperparameter tuning often needed to get good predictive performance. And that's a familiar problem with machine learning. The other problem, though, is that machine learning predictive models are designed to give you an accurate point prediction. And that's not what we're looking for. So the basic thing that these models are trying to optimize is somewhat wrong. They're trying to get the best guess. They're not trying to model all the variability and uncertainty. So we've been doing a number of things. This is me and some PhD students. So Agnes has nearly finished her PhD. Kieran started about a year ago. So Agnes has been looking at XGBoost, which is a prediction method that fits linear combinations of trees, small trees, to get a predictive model. And it's nice. It's one of the better black box prediction algorithms out there. I mean, boosting has been a good standard black box approach since it was invented, and XGBoost is a little bit better than the previous boosting systems. We have, and that gets a point prediction. There's then predictive mean matching, then says, how do we get the residual variability around that point prediction? And predictive mean matching says we want to pick an observation that we've already got that has a similar predicted mean to the mean we just predicted for the missing observation. There's various versions of that depending on exactly how you set up the closeness. And then the other sort of uncertainty we need is model uncertainty, that there's uncertainty in the fitted XGBoost model. In the classical multiple imputation framework, that's handled with Bayesian by looking at posterior distributions. Not in a position to do that here, but we do it by resampling and refitting the model. And XGBoost is fast enough that we can afford to do that. And it turns out to work really reasonably well. For small data sets, you're better off using the standard approaches, but for large data sets, it's faster, and if their relationships are complicated, it's also more accurate. And we've got a paper coming out in the Journal of Computational and Graphical Statistics about that. We're also interested, so then you've got questions like, how do you do model checking for these complicated models? And it's a bit limited, but you can at least look at variables a few, one or two or three at a time to see how well they match. The imputed distributions match the observed distributions. So here we're getting reasonably good match. We've got the observed data and 5 sets of imputed data for a pair of variables. And, looks pretty nice. But in general, so you can do sort of low-dimensional checking. High-dimensional checking is hard because you can't look at things in high dimensions, and things aren't close in high dimensions even if you can. If you've got a high-dimensional thing, then the generic low-dimensional projection of it is just a blob. And
Thomas?
Yeah?
The variability in the BMP head in the observed data is greater than in
Yes.
the others. Is that because your model's estimating some statistic in the others? Or?
No, it's just, it really would be better if it was more variable. So this is not a particularly good fit. And then the second wave of this is to look at neural network models for doing multiple imputation. There's 2 classes of models we've been looking at. One is autoencoders, which work by basically principal components. If you're a statistician, it's a sort of non-linear version of principal components. You squash the data down to a low-dimensional space and then blow it up again back to the original space, and assume that everything that doesn't fit in that low-dimensional bottleneck is noise. It's been used as a way of denoising pictures for forever with the linear case. And so we've done that. There's 2 flavors of autoencoders that we've used. And that works sort of, but it's too sensitive to hyperparameters. The literature on both of these is optimistic about accuracy and the sensitivity to tuning. Anyway, so we've got that. We liked variational autoencoders as a possibility, but it turns out that they aren't as good as they're made out to be. The other area is generalized adversarial networks. So these were what were being used. These were the previous generation of things being used to produce pictures. Imaginary art or dogs or whatever. And they have 2 parts. There's a model that generates pictures, and then there's a model that gets given a generated picture and a real one and has to say which one is which. And they train each other. So the generating model gets good at making things that look real, and the discriminating model gets good at deciding whether they're real or not. And they train each other, you hope. And so we want to use it to make up data. There's a small literature on this at the moment. And again, it seems to be a bit optimistic as to the accuracy that's achievable. We in particular want to use it for fairly large amounts of missing data, including data missing by design in medical studies. And the predictions tend to sort of collapse with large amounts of missing data. So this is 5 copies of a scatter plot of 2 variables from a GAN. And you can see that each of those curves is from one neuron in a neural network, and it's just not working. This was admittedly with 90% missing data, so it's not an easy problem. But on the other hand, we're trying for data, not Miro posters or whatever. So it is a bit unsatisfactory. So that's what we're still working on, is imputing lots of data when it's missing by design in medical studies. And we've got comparing various machine learning approaches and various classical approaches for doing it. Thank you. Question, yeah.
For those scenarios where you're missing 90% of the data, how do you calculate the accuracy and how do you decide which hyperparameters to use?
Okay, so there's 2 things. One is how do we calculate whether it's working or not? We do that because we know what the data looks like. It's simulated. How do you in production do it? So what you do is you look at you basically have to introduce more missing data. So you take the data you've got and make some of it go away, and then you know what that data looks like because you've already got it. So the way you can produce the training is by masking out some of the data you've got and asking the algorithm to impute that. And if you had 90% missing data in a small data set, there wouldn't be much left when you did that. But if you've got, 100,000 points and 90% missing, that's still 10,000 points. So it's still feasible to do this sort of thing.
And do you choose the hyperparameters depending on the accuracy of the result?
Yes, that's the idea. So we want to choose them. We actually choose them based on... so there's a number of possibilities. One is to just choose them based on the predictive accuracy, which is the simple thing to do and isn't quite right because predictive accuracy isn't what we care about. But that gets you reasonably good choices, and then we can look at fitting a model to the data and getting the unbiased estimation in that model as a sort of secondary criterion. So when we're trying to tell how well a method works, what we care about is if you fitted a model to these data, do you get the right model? If you fitted, say, a linear regression to those, would you get the right linear regression? And that's our assessment of whether it's working, but the internal assessment is based on predictive accuracy. And we're looking at ways of modifying the loss function so that it isn't just based on predictive accuracy in the hope that it will stop this happening. Yep,
Thomas, you tried dropout methods?
yes. So that both of the autoencoders, we've tried dropout, and it actually doesn't help. I expected it to be good. I mean, it's a pretty good regularization method, but it turns out to be less successful here for the autoencoders than we'd expected.
Yeah, because we had much better experience with dropout rather than variation method. When
yeah.
adding, variation certainly.
Yeah.
Yeah, that's
Yeah.
interesting.
Yeah. Kathy? Yeah.
How does the pattern of missingness affect? I mean, because this all depends on how many variables and what percentage of your values are missing for different variables.
So one of the methods that we're looking at that's from the literature actually also tries to learn the missingness pattern, so that you've got a binary. It's basically a binary missing non-missing regression, and it's got a separate neural network that tries to model that. So that's for when you've really got missing data. For the missing by design setting, we know what the structure is, and so you don't need to learn it because we know what it is. But yeah.
Just curious here, if we flip the narrative here, and let's say it's missing by design in a medical situation,
Yep.
and the data is anonymized
Yep.
by design, and someone gets hold of 10,000 data points in dark
Yep.
web.
Yep.
How easy will it be to use one of these methods to reverse engineer another 10,000 points?
So they won't be, I mean, you can easily reverse engineer another 10,000 points. What they won't be is points that correspond to real people. And so there'll be, so there won't be any privacy loss for real people because there won't be any link. So you'll, what's more of a concern is that you might, this means that suppressing individual variables may not be very effective as a privacy measure. Because if you just suppress a few variables, it may be possible to reconstruct them. And so this gets you closer. I mean, in a sense, what you want to do with suppression and privacy is to reduce, you want to control the sort of maximum possible information that someone can have. And this is an algorithm that gets you closer to knowing what that maximum possible information is, but it doesn't increase the information. So this is information that's already there. It just makes it easier to do the computation to work out how close it is. So if you've got some method that gives you guarantees on information, this won't break those guarantees, but it will get you closer to be able to compute that, that bound. I think that in a lot of cases, the methods with guarantees will be too strong to let you do anything. And so you do need a certain amount. I think for practical high-dimensional applications, you need a certain amount of trust anyway, because the methods that come with strong enough guarantees to not need trust also stop you doing very much with the data. So, I think that the attempts to bypass the need for trust aren't going to really work. But yeah.
So I have two simple questions. One is for the categorical data, you can easily decide which value is the candidate for multiple iteration.
Yeah.
But for continuous variables, how do you decide the candidate?
Oh. So, so that's the predictive mean matching thing I talked about. So you end up with a predicted value for each missing observation, and you look at other observations that you weren't missing that have similar predicted values, and you pick and you use those as your candidates. And so that makes sure that you will only impute values that actually exist in the data. And that's a problem in small data sets because you want to be able to impute values that don't exist in the data. But in large data sets, it's actually pretty good.
My second question is that you mentioned when a relationship among variables is more complex, this methodology becomes better. Why?
It's not so much that this methodology performs better in complex relationships as that the competitors perform worse. So the sort of state-of-the-art method is called mice, and it fits generalized linear models to each variable given all the others. So it models what we call the full conditional distributions, but it assumes the full conditional distributions have that generalized linear model form. And if you've got a lot of, the more variables you have, the stronger an assumption that is, and the more that you'd want to be able to have a more complicated space of models and then regularization to avoid overfitting within that space. And so if you've got little data sets of 500 observations and 10 variables, it works pretty well. But if you've got 1,000 variables and 1 million observations, then mice isn't so satisfactory.
Okay, let's thank Thomas.